So today we're going to talk about continuous review systems. Last class on Monday we talked about periodic review systems, and basically those were the systems where you're placing an order every 2 weeks or so. The continuous review systems are slightly different in that those are models where we are constantly monitoring our inventory levels, and when our inventory reaches a certain point, that's then the trigger that says we need to place a new order for more parts. So that point in terms of our inventory level is called a reorder point. So when inventory gets down to that reorder point, that's our trigger to place an order, and it's always going to be for the same number of units, which is going to be what we solve for later in terms of Q. So these systems, again, you're constantly monitoring your inventory, so that's why it's called a continuous review system. Again, your every order is going to be for Q units, and then we're going to be able to include safety stock in our reorder point in order to make sure that ideally we don't run out of inventory in this type of model. So the variables that are used in the continuous review system are shown on the slide now. So this one should probably be called variables, not assumptions. A lowercase d is our demand per period, and it's always going to be a constant number. The capital D then is our annual demand number. L represents our lead time. So again, that's how long between when we place an order until it arrives at our site. The H is the holding cost. That is an annual number, so it's saying how much does it cost for us to hold that inventory because it's not free to hold inventory. S then is the cost of placing an order, so it's either referenced as the ordering cost or the setup cost if it's a cost, a part that we make ourselves. And then finally P is the price of each unit. The basic assumptions then of the EOQ model is that demand is known, constant, and independent. So again, we said that the demand on the last slide is always the same. We know exactly what it is, and we're saying that there's never going to be any variation in that. And that's going to come in handy when we look at one of the graphs coming up. Lead time is known and constant. So again, we know exactly how long it's going to take for our supplier to ship a part to us, and there's never going to be any variation on that. The next one is a little unrealistic. So it says receipt of inventory is instantaneous and complete. So what that's saying is that as soon as we receive those parts at the end of the lead time from the supplier, it is all there and all available for us to use as soon as it comes into our dock. So again, not realistic. Most companies have to take some time to get those parts in, count them, put them out on the shelf so that we can use them, but it makes our modeling here a little bit easier. We're going to say for right now, quantity discounts aren't possible. So we talked about them on Monday, so that's when you order more parts, your price goes down per unit. That is not feasible in this situation. The only costs we're going to be concerned about in this model are the setup and holding costs. So we're not going to look at any other types of cost. And again, we're going to assume because of the fact demand is known and constant, there's no variation, that we can totally avoid stockouts due to those assumptions. So this is then what the continuous review system model looks like. It's often called a sawtooth graph because it looks like if you saw one of those old saws that we're using, those teeth on the saw. Basically what we're saying here is that demand is constant and known, so that is how we're getting our straight line here. So that's where our demand is known, it's constant, it gives us the straight line. This point here is our reorder point. So once our inventory reaches that level, that's the trigger that we place an order. It's going to take the lead time in order for that part to come in. And since lead time is constant, the way this is set up is so that as soon as our inventory reaches 0, we get our parts in, and that's for Q units. And again, it's instantaneous and complete. So as soon as that day hits, we get all of our parts here, and they're ready for us to use. And again, the model is just going to continue out. It's always going to be the same distance in this case because of the fact that we know what demand is and it's constant and known. So in order then to figure out how much we're going to order, we're going to look at our holding costs and our setup costs, and we're going to look at them on an annual basis. So the total yearly holding costs. So if we look here at that number, so let's just switch here. So our holding costs is this Q divided by 2 times H. So it's this whole portion here. And then our setup costs or our ordering costs are this portion of the equation here. So basically what this is saying is the Q divided by 2, so if we go back to our blue here, that the average inventory level is Q divided by 2. So that's that portion here is our average inventory level. The number of orders that we're going to place on a yearly basis, that's just the Q divided by it's the annual demand divided by Q. So that's going to be how many orders we place a year, multiply it by the number of orders that we're going to place. Now, what we're going to do is set those two equations equal to each other. So right now it says our total cost for the year, our annual holding cost, and our annual setup cost. If we set all of that together and solve for Q, that's going to be our economic order quantity, which is what we show on the next slide here. So basically the economic order quantity is going to be that order level, which is minimizing our total annual cost in terms of our holding costs and ordering costs. So the variables are all the same that we've already seen. So our economic order quantity is going to be 2 times annual demand times that setup cost divided by the holding cost and taking the square root of all of that. So if we look at it graphically here, basically again, our holding costs are going to increase on a linear basis based upon the fact that it's our annual or our average inventory divided by the holding cost. Our setup costs are this green line, which are decreasing, and what we're going to see is that's getting less as our order quantity gets bigger because of the fact that we're going to be placing less orders. So the point where those two lines intersect, when we add them together, it gives us that total cost line. So at that point, that is the minimum point in terms of total cost. So it's going to then be our EOQ is going to be the point that minimizes our overall annual costs. And again, that EOQ is the Q value for how many units you're placing in each order. So if we look at a simple formula here or a simple example here, basically this one has all the variables already identified for you. So our annual demand is 2,000 units. The holding cost on an annual basis is $10 per unit per year. The ordering cost is $25 per order. So each time we place an order, it costs us $25. First thing we want to do then is solve for Q. So again, we're going to be using our formula up here. So Q then is going to be equal to 2 times our annual demand of 2,000 times our setup cost of $25 divided by our holding cost of $10 and taking the square root of all that. So when we solve for that, it's 100 units. Remember, we're talking about units here, so if that happened to come out to a fraction, you're always going to round up to the next whole number. To get our total cost then, it's going to be this equation up at the top here. So it's going to be Q divided by 2, so 100 divided by 2 times our holding cost of $10 plus our annual demand of 2,000 divided by Q, which is again 100, multiplied by our ordering cost of $25, and you're going to see that this comes out to be $1,000. So remember, your total cost is in dollars, so it is possible to have fractions here because of the fact that we are talking about dollars and cents. The next thing we need to consider then is what exactly is that reorder point? So how do we calculate that trigger to know it's time to place an order for Q units? When we assume demand and lead time are constant, there's never going to be any variation. That's when you use this very simplified equation. When we realize that, again, there's going to be some variation in the real world, that's when we're going to include safety stock. And we'll go over the reasons in terms of why you might have safety stock in class. We talked about it slightly in class on Monday, but we'll go into more detail what's in your slides when we get to class on Friday. So again, this way you can see our model has changed slightly when we're looking at it. So our line here is no longer a straight line. So remember before, this was a straight line. When we hit the reorder point, it would take us out to lead time and our parts would come in. So again, this is for Q units. Both of these lines here are for the same amount. The difference now is that, again, we've hit our trigger of our reorder point, but now you can see our line is no longer constant. So what's happening is we're placing our order. In this case, it looks like it's taken a little bit longer than we expected. Demand was a little bit more than we thought, and that's why we've dipped down. And you can see this bottom portion here is our safety stock. So we've dipped into our safety stock, but we didn't run out of any inventory. Again, our order came in for Q units. We went up here by Q. We use it. It's not in a constant manner, but again, when we hit that reorder point, that's our trigger. In this case, it took a lot longer for those parts to come in, but demand wasn't as great. So in this case, you can see that our inventory went up above the Q value plus safety stock. So our graphs are no longer going to be as kind of perfect as they were before because we're accounting for some of the variability that exists in the real world in terms of what demand is and the lead time from our suppliers. So in order to calculate that safety stock level, so that was that bottom portion of the graph, so it's that extra inventory we're holding just in case something goes wrong, it's going to be a Z-score, and we'll go over how to look that up in class on Friday. But basically, again, it's the number of standard deviations that you're looking at from that average. And then the higher the Z-score, the lower the value, the probability of a stock out. So we talked about this in class, that if you choose a Z-score that says you want a 95% customer service level, that's saying you have a 5% chance of a stock out. So we're going to look up the Z-score in our table, and then what you're going to do is take the square root of everything that's past that. So you're considering your lead time, the variance of demand, the variance of lead time, and what your average demand is. Make sure you notice here that these are variances. So a lot of times the equations will give it to you as standard deviation, and in that case, so your standard deviation, just as a reminder here, is just going to be like sigma L or sigma D. So remember, in those cases, that's a horrible sigma, but you get the point. But basically what we're saying is in those situations, you're going to have to square these values in order to get the variance. So just make sure you are aware of that difference. So then to get our reorder point with safety stock, we're looking at the average demand over the lead time. So that's what this first portion is. And then again, this whole portion here is our safety stock. So if a question just asks you for safety stock, you're just going to do that second half of the equation, but usually you're going to have to calculate your reorder point as well, which is going to include all of it. So if we go through our example here, try and highlight which each of these variables are. So our daily demand in this case is D bar. The standard deviation, so again, this is just going to be sigma D. Our lead time is the L bar. Standard deviation of lead time is sigma L. Our service level is 95%, so that's going to say Z is equal to 1.65. Again, you can look that up in Appendix 1 of your textbook. We also went over it in class on Monday when we did the restocking level, and I'll show you again in class on Friday how to do that. So the first part is asking about safety stock. So remember, that's just this part of the equation is safety stock. So it's going to be the safety stock is 1.65. I'm sure you can see that point there, times the square root of our average lead time, which is 5. Sigma D we said was 3, so we're going to have to square that, plus the average demand is 15, so we're going to square that, times the sigma L was 2, and again we have to square that. So when we go through that, we get 50.7. Again, we need to round that up to 51 units because we can't have a fraction of a unit. So our reorder point then is going to be the average demand of 15 times our average lead time of 5 days plus our safety stock, which we just figured out was 51. So in this case, this is going to come out to be 126 units. So then what we're going to do in class on Friday as we continue with inventory is start to look at some other variations of these continuous review systems, such as like what happens when we actually do consider that there's quantity discounts. How do we take that into account in terms of determining what is the ideal level of Q that we should order?